Hi everyone, my name is Kyuhan, and I'm presenting our work SSumM, Sparse Summarization of Massive Graphs. Graphs are everywhere, and various information can be modeled with graphs. For example, graphs naturally represent subway networks, citation networks, and internet topologies. As the underlying data are accumulated rapidly, massive graphs have appeared. Social networks, purchase histories, and the World Wide Web, to name them few. They have millions or billions of nodes and edges, and their numbers are exponentially growing, even at this moment. However, despite the abundance of graph research, many existing tools are inapplicable to such massive graphs. This is often due to computational costs increasing rapidly with respect to the size of graphs, that is, the number of nodes and edges. Moreover, massive graphs do not fit into main memories, causing I/O delays in disks and networks, which slows down the speed of query processing and analysis. We can tackle these computational and storage challenges through graph summarization, where we aim to preserve the essential structure of a graph while shrinking its size by removing minor details. There do exist other graph compression methods such as the Web Graph Framework, BFS encoding, /burn, and VOG. However, graph summarization stands out among a variety of graph compression techniques. First, it is elastic. We can reduce the size of outputs as much as we want at the expense of increasing reconstruction errors. Second, it is analyzable. Since the output of some graph summarization is also a graph, existing graph analysis and visualization tools can easily be applied. Lastly, it is combinable for additional compression. Due to the same reason, the output summary graph can be further compressed using any graph compression techniques. Let me give you an example of graph summarization with an input graph with 9 nodes and 16 edges. Suppose node 1 and 2 are grouped together, and the other 3, 4, 5, 6 are grouped, and the other 7, 8, 9 are grouped. We call this group of nodes as a supernode, which is a disjoint and exhaustive subset of nodes. To distinguish nodes from the input graph and the summary graph supernode, we name them subnodes. For the same reason, we name edges in the input graph subedges. The connection between supernodes is called a superedge, which has the weight that corresponds to the number of subedges between the two supernodes. For instance, since there are 3 subedges between supernodes V1 and V3, the weight of the superedge is 3. The other superedges and their weight are set the same. Note that for conciseness, some superedges can be dropped. From this summary graph, we can reconstruct the weighted adjacency matrix, which we name them reconstructed summary graph G hat. Each element for the reconstructed adjacency matrix is computed using this equation. The denominator is the maximum number of subedges between two supernodes, and the denominator is the actual number of subedges between two supernodes. In this case, supernode V1 and supernode V3 can be connected with at most 8 subedges between them, since they consist of supernode 1, 2, subnode 1, 2, and 3, 4, 5, 6 respectively. The actual number of connections between them is 3. All corresponding elements in the reconstructed adjacency matrix is set to 3 over 8. Let me formally define the graph summarization problem. Here is a definition that is widely considered as the graph summarization problem. Given a graph G and the target number node K, the objective is to find a summarized graph G bar that has K nodes, such that it minimizes the difference between graph G and the restored graph G hat from the summary graph G bar. Note that here we concern only the number of nodes, not the exact size of the summary graphs in bits. However, it is not trivial to control the number of nodes so that a summary graph tightly fits in target storage. This is because how the size of summary graphs changes depending on the number of nodes varies across datasets. In this work, we consider a new practical problem. Different from the existing graph summarization problem, where the number of nodes in a summary graph is constrained, we constrain the size in bits of a summary graph. By constraining the size in bits, we can easily make summary graphs tightly fit in target storage. Given a graph G and the desired size K in bits, our goal is to find a summary graph G bar whose size in bits is less than K so that it minimizes the difference with the graph G and the restored graph G hat from the summary graph G bar. In the following slides, we define the size and the difference. For measuring sizes, we assume that the summary graphs are stored as an edge list. The bitwise cost for storing a graph in the edge list format is given here. Each edge consists of two nodes, each of which is encoded using binary log of number of members of 3 bits. We define the size in bits of summary graphs based on the assumption that they are also stored in the edge list format. The size in bits of the summary graph G bar is given here. WSUM max denotes the maximum superedge weight. The first term is for the number of members of P superedges, which are encoded with 2 supernodes, and its assigned weight, which are encoded using 2 binary log of number of members of S and binary log of WSUM max bits, respectively. The second term is for storing membership information. Each subnode belongs to a single supernode, which is encoded using binary log of number of members of S bits. For measuring the difference between an input graph G and the restored graph G bar, we used L1 and L2 reconstruction error between adjacency matrix of an input graph G and the reconstructed adjacency matrix A hat obtained from the summary graph G bar. Now that we have formally defined our graph summarization problem, we present SSumM, a fast, compact, and linearly scalable solution. SSumM is based on 3 main ideas. First, SSumM smoothly combines node grouping and edge sparsification, 2 widely used compression strategies. Second, SSumM prunes search space by focusing on promising node pairs to be merged. Lastly, during the search, SSumM carefully balances the reconstruction error and size of the summary graph using the minimum discretion length principle. To maximize the compression performance, SSumM merges supernodes into a single supernode and at the same time sparsifies the summary graph. For example, these 2 supernodes are merged into a single supernode. We then create the superedges adjacent to those supernodes and carefully drop some of them, considering the objective function, which will be explained in the next slide. The graph summarization problem can be thought of as a search problem, as shown in this example. We start a search from the input graph, and we choose next actions repeatedly until we reach a desirable summary graph. How should we choose a next action? That is, a next summary graph. To this end, we use the MDL principle. The principle states that given data, the best model for the data is the one that minimizes the discretion length. In our case, data is an input graph G, and the model we are trying to find is G bar, a summary graph. The discretion length is divided into the model cost and the data cost. The model cost measures the number of bits required to represent G bar, while the data cost measures the number of bits required to describe G given G bar, or equivalently to describe the difference between G and G bar. Thus, the data cost is naturally interpreted as the reconstruction error of G bar in bits. Our proposed algorithm SSumM uses this cost function to balance the size and reconstruction error and thus to measure the quality of candidate summary graphs. Given an input graph G, the desired size K in bits of the summary graph, and the number of T of iterations, SSumM produces a summary graph G bar. T denotes the maximum number of iterations. SSumM repeats 2 phases until the number of iterations reaches T or the size in bits of the summary graph is below K. If the size in bits of the summary graph is still bigger than the desired size K, SSumM runs the further sparsification phase. SSumM first initializes G bar to G. Each subnode in G is regarded as a supernode in G bar. Similarly, each sub-edge is regarded as a superedge. Merging two randomly chosen supernodes is unlikely to reduce the cost function. Thus, in the candidate generation phase, we search for sets of supernodes whose merger is likely to significantly reduce the cost function. We call such sets candidate sets. Each candidate set consists of supernodes that are within two hops of each other. Among all possible supernode pairs in each candidate set, whose size is C, SSumM randomly chooses binary log of number of members of C supernode pairs. For example, in the candidate set in the figure, there are 10 possible pairs. Among those 10 pairs, we sample 3 supernode pairs. Among the sampled pairs, SSumM selects one that leads to the greatest reduction in the cost function. In this case, supernodes C and D are such a pair. If the reduction exceeds a threshold zeta, the supernode pair is merged into a single supernode. Otherwise, we sample new binary log of number of members of C pairs and repeat the process until the reduction does not exceed the threshold max of binary log of number of members of C or 1 times in a row. Once supernodes C and D are merged into a new supernode, all superedges adjacent to new supernode are selectively created or equivalently sparsified so that the cost function with respect to this new supernode is minimized. This merge and sparsification phase is repeated for every candidate set. After that, SSumM repeats the candidate generation phase and the merge and sparsification phase until the size in bits of the summary graph becomes smaller than the desired size k. The candidate set generation is a randomized process, and in each iteration, we obtain different candidate sets. Inspired by simulated annealing, we decrease the threshold zeta over iterations, balancing the exploration of the current candidate sets and exploration of new candidate sets. If the size in bits of the summary graph is still greater than the desired size k after t iterations, SSumM runs the further sparsification phase. In this phase, SSumM drops superedges greedily, while increasing the reconstruction error as little as possible, until the size in bits of the summary graph becomes smaller than the desired size k. I've covered detailed concepts of SSumM. Now let me share experimental results about SSumM. We performed experiments on 10 real-world graphs with up to 0.8 billion edges. Datasets include web graphs, social networks, collaboration networks, and email networks. We compared SSumM with 3 existing algorithms for graph summarization: K-graphs, S2L, and SAAGS. We compared the size and reconstruction error of the summary graphs obtained by SSumM and its competitors. SSumM yields compact and accurate summary graphs. For example, in the Amazon purchase history, SSumM yielded up to 11.2 times smaller summary graphs than the best competitor with similar reconstruction error. It also achieved up to 4.2 times smaller reconstruction error than the best competitor with similarly concise outputs. Note that most competitors ran out of memory, requiring more than 64 GB RAM, and ran out of time, taking more than 12 hours. In all datasets, SSumM consistently yielded the most accurate and concise summary graphs. We compared SSumM and its competitors in terms of speed and the quality of summary graphs. The quality of summary graph is a metric for evaluating the quality and size at the same time. As shown in the figure, SSumM gave the best trade-off between speed and the quality of the output summary graph. Specifically, SSumM was up to 406.6 times faster than the competitors with outputs of better quality. In all datasets, SSumM consistently provided the best trade-off between speed and quality. We evaluated the scalability of SSumM by measuring how its runtime changes depending on the size of the input graph. We randomly sampled a different number of nodes to obtain various sizes of graphs from the Skitter and LiveJournal datasets. As seen in the figure, SSumM scaled linearly with the size of the input graph. Notably, due to its scalability, SSumM successfully summarized a 26 times larger dataset with 0.8 billion edges than the best competitors. We measured how the size of iteration t in SSumM affects the reconstruction error and of its summary graph. As seen in this figure, the reconstruction error decreased over iterations and eventually converged. More iterations were needed for convergence as the target size decreased. However, in all settings, 20 iterations were enough for convergence. Here are three main contributions of our work. First, we formulate a practical variant of graph summarization problem, where we constrain the size and bits of the summary graph, not the number of nodes in it. Second, we propose SSumM, a fast, accurate, and linearly scalable algorithm for the new problem. Lastly, we validate the advantages of SSumM over its state-of-the-art competitors throughout extensive experiments on 10 real-world graphs. The source code used in the paper is available in my GitHub repository. Please check out our paper for more details. Thanks for watching.